CE. CE, or actually C of the B. This should be CE, is the parallel capacitor. This capacitor makes the transistor work like a common emitter amplifier. There will be no signal at the emitter because capacitor will be a short. Under the right calculation, under the correct calculation, we can make that to be negligible, shorting literally the signals over there. Then, that capacitor will be short. Therefore, AC signal in here will couple into the base. So there is a DC in here, but because we have an input resistance, we will have a coupling at that point. Then, there will be a fluctuation in here, as well as a DC, DCs that we established. We want to transfer the fluctuation over here, but not the DC, because DC means constant. A constant voltage doesn't carry any information. Information is in the fluctuation, waveforms, speech, picture, everything. So we need that capacitor in order to block the DC reaching the load, but the signal, which is intelligence, somehow reach the load resistance. VI is called input voltage to the circuit. So this is your main amplifier. VI is this net input voltage reaching there. VI is different from the signal, VC, because if that source happens to have a resistance in there, RS, it forms a voltage divider with the input. So signal in here might be large, but signal here can be smaller because input resistance attenuates. It reduces the original source signal. And that is the reason why we want to have a relatively higher input impedance so we don't lose much of the signal over here. So this is the VI actually, and that is the VS, the signal. Here, V signal, that's the V input. A captured portion of the VS. And then it's that signal that we will amplify, get it enhanced at the output. So it says the significance of each capacitor, and here. This is the red one is the DC load line. So remember we have VCC minus VE, which is the VE you have chosen in here, VE, that's the floor, it's a set value. So IC and the VCE with the VE as a constant, with the VCC as a supply. In terms of the DC values of IC, it has a route, it has a relationship, which moves along this red load line here. This is the foot of the load line, where the transistor will go into a cutoff. And this is the top of the load line, where transistor will go into saturation. That's called DC load line. The DC load line must be chosen in advance, and it does not determine the actual swing, how much it will swing. That means how much AC voltage and the current will move in the plane of the transistor. Remember, this is the transistor plane, IC-VCE plane. So we're going to move in that plane under the signal. In terms of DC, you will move along the red one, known as DC load line. But in terms of the AC, it's a different game. You will move along the black one. The slope of that load line is no more 1 over RC, like that one, but it's changed into 1 over RC parallel with RL. Because under the AC condition, the capacitor at the top, this capacitor shorts, therefore RC goes parallel with RL. That is why the AC load line will move from the Q point, set DC point, along the black one. This chunk here, the movement from the Q point to the top, known as positive swing. It will determine this part, magnitude of that part, before transistor reaching cutoff, this cutoff. This is the cutoff. So the old cutoff point, notice, the old cutoff point will move from its place to here. The cutoff point pertaining to the DC load line will move here. So the amount that you can signal the transistor before reaching into a cutoff is this much, P, which is base of that right angle triangle. Because you know the slope of this line is equal to that from the AC model, and we know IC quiescent, we can show you that the P quantity is ICQ multiplied by RC parallel RL. So this will be the positive swing, this swing coming across the load resistor, the output, amplitude of the positive swing, available from the amplifier. On the negative side, to the left, which we move up the black load line, we approach towards the saturation. Saturation is around here. So this chunk in here, horizontally from here to here, is your negative swing. This is the negative swing. Magnitude of the N, I marked it here, N, this one as P. So the value of the N, the throw, is this chunk here, which is simply that coordinate on the VC minus of 0.7. So we come up to an interesting equation which will predict for us how much positive swing is available, how much negative swing is available across the load resistor, which of course in a sinusoidal way both should be symmetrical. So two quantities can be calculated, the P from biasing, watch here, and the RC and RL, and also the VCE choice you made initially. When I said VC IC will be given, I'm afraid nobody is going to give that to you if you're in an office. You've got to make your own choice, see, to provide that amplitude swing. So you will use your own experience. You don't want to put it too close to the top, too close to the bottom here, too close to the top here. If you put your Q point when you were doing the DC analysis along the red line here, it's a bad choice, because there will be very little room from that side and also from this side. And ideally speaking, the best place to put the Q in the DC load line is somewhere that it will be nearly in the center of the AC load line. See, this is the two chunks of the AC load line, from here to here, here to here. If you could equalize P and an N, in other words, putting that dot in the center of this part of the load line, you can get a maximum swing for the N and the P. That's the smart design. Largest possible amplitude at the output. Although, placing the Q in here, almost in the center there, is right there on the DC load line. So remember in the beginning when you started putting the operating point in the middle of the DC load line? All right? It's just like a spoon feeding you in the beginning, giving you soft stuff to eat until you can chew the real steak, okay? So it's just to tell you, look, it's easy. If there's only one DC load line, yes, you put it only there. But making an amplifier with an RC and not having a load, what's the point of it? You've got to have a load. Load is the destination for the power. This load here, RL, is the one that has to receive a good chunk signal, good large signal. So don't blame the teacher at that point when he said you put in the middle of the DC load line. That's kind of true if you're playing, like kid game. But when it comes to real designing an amplifier, no. You've got to put it in the center of the AC load line. Okay. So here are the two equations. It's very simple. RC parallel RL times ICQ will determine the positive swing, and VCQ minus 0.7, which is this chunk here, this segment, here to here, will give you the negative swing, this part, the black part. Let me go now to the next one. Okay, now distortion. So it explains the distortion. That if you try to apply a very large signal, really go all the way to the N, to the P, I tell you what will happen. The circuit won't be linear because it's an exponential device, transistor. It will start making your signal look crooked. So it won't be a nice sine wave, symmetrical. It will be round at the top and short, tall at the bottom and sharp. So it will go like this. VO will look like this. Will look like that. Okay, this is when cutting off here. Cut off, about to cut off, getting close to the cutoff. This is close to saturation. In other words, when you're getting close to saturation, to the left of the coupon. So it will look like that. Although the NPP calculates the swing, possible swing N and the P, giving you a size, but it's not a useful limit. Maybe you use half of it. It's good enough, you see? So if your N and the P calculation tells you, oh, you can get 7 volt peak to peak out of the output, you can get 7 volt peak to peak, but you see quality of the signal will be lost. You'll get too much distortion there. You use maybe 50% of that maximum. It's a practical one, 50%. So if it's a 7 volt, don't drive it to more than 3.5 volt peak to peak at the output. Keep it, to that limit. Okay, small signal model. So how does that work? It's pretty much straightforward here. So this is the model. Let's see how it evolved. And then the equations will come out one after the other. So I will draw the original circuit quickly, very quickly. This is the original circuit. Signal VS. This is RS. You have the capacitor C1, and then R1, and then R2, and then R1, VCC. Up there, transistor RE. This is known as CE or CB sometimes. CB, bypass capacitor. CE meaning it's the capacitor grounding the E. Then you have RC up here. C2, output coupling capacitor. You get load resistance RL, and this is your output voltage VO. This is the V up. So we want to translate that into a model. Translate this into an AC model, which is here. All the details. So don't draw it. There's no need for it. Just follow the board. I will move my cursor over it. So you start with VS, which is this guy, because you have signal there. You will put all the DC voltages to short, all the DC voltages that exist in the circuit, and the capacitors into short. So all capacitors short, all DC voltages short. They are not moving, they are zeros. So here, this is not short because it's fluctuating, it's a signal. So you start here, that's the signal. RS, you have an input. It will not be zero there. You have a signal in here. Here, you see this chunk I put it there, X sub C equal to 0. This is the short. This is a short, which is X sub C1. Then you are now here. Okay. from here, R2 goes to ground. There's no doubt, there's no signal on the ground. So you put R2. Here, there is an R1. R1 goes to, ends at the VCC, but VCC is not changing, so it's considered ground. VCC, those that don't change, considered ground. So this is signal-wise grounded. That's why you will see it in this form. Otherwise, there was a power supply here. Remember, it's superposition. We have DCs in here, then AC, two different sources. DC superimposes its own for the sake of biasing. AC superimposes its own because of the signal that you are putting in. One at a time, we analyze. So you come to here, that's the transistor, this chunk here. B is the base, that's the R pi. We learned how to calculate that. This source is the beta times IB, or even better, GM times VBE. This works better. I'll tell you why it works better. GM times VBE. But no problem, you could have replaced IC with beta multiplied by IB. Then you have to calculate the current in here, if you did that. Okay, so I chose this one, GM times VBE, for the current source. Then you have RO, which is the collector to emitter resistance of transistor, and that is coming from those slopes. Remember, RO is equal to VCE quiescent plus the early voltage divided by IC quiescent. That's the dynamic resistance between conductor and the emitter. If you have it, you put it there. Usually this resistance is so high in the 100K that it dominates over RC, which is order of 1 or 2K. So a 100K parallel to 1 or 2K, it just doesn't matter. You see, you just take RC and whatever RL. So that is why, almost without exception, you come to a problem, you assume RO is infinity. And I will tell you, assume VA is infinity. It means this number is infinity. That means then RO will be infinity as if it's not there. So you will add that here in case if it was given in here. Then from the collector, from here, you've got RC. End of the RC is connected to supply, which is ground. So you must have a resistance RC going from collector to ground. Here you are. This is the one. Then, other side of the RC, this side of the RC, there is a capacitor there, C2. This capacitor is another short, X of C2 equal to C, another short. At high frequency, there is no voltage drop. So you're assuming capacitor is large. But I tell you what, there's a DC voltage on it. There's a DC on it. The DC is equal to V of the C, whatever the DC voltage is there with respect to the ground. DC voltage here is 0 because it's the load. There's no DC voltage over there. So this thing, this capacitor, gentlemen, it acts like a battery. Watch here. Because it is fully charged like a battery. And what did we do with the batteries? Didn't we short? That's why we shorted this battery in the model, you see? That's why we shorted that. Otherwise, it's a battery. Its value is VC, whatever the bias was. 8-volt bias there, it's like 8-volt charge battery, already it's charged. So you put a short there, and finally RL to the ground from the other end of it. And this one, which is the big question in here. What happened to RE? We have an RE there, but why it doesn't show? Because this is shorting the RE. So it doesn't let RE to carry any signal. No signal whatsoever on RE. But you know what you have? Here you have like that 2-volt battery. You remember the VE equal to 2 volt? It's in. But you are taking it as a short. So that is the concept of equivalent circuits. That when you come to drawing your equivalent circuit, you take care of those DC values by shorting the capacitors, because it's like a charged battery capacitor that is charged to the level of a battery, but steady. DC is steady. No more signal on it. There can be current through that capacitor, but no signal on it. Indeed, there can be a current through this, and there is a current going through that short, but it induces no voltage on it because its reactance is zero. And this will be our model finished from here to the ground. Now, finding the voltage gain. I'm going to relate voltage gain AVI. AVI means ratio of that amplitude VO divided by the voltage here, which is here. Input voltage. It's not the same as voltage here. It's different. There's a source resistance in between. So, final destination is to link VO to the VI, and then link VI into VS, which can be done very easily. So this is the procedure. What is the input impedance, Ri? Input impedance Ri is defined as how much current is taken through the RS, how much voltage you have at that node, VI. VI over II is called input impedance, Ri. Ri is equal to, that's so simple. Look in the direction of that arrow, you see R1 parallel R2 parallel R5. Do you see that? That's it. It's a simplified one because this is a simple circuit with all three in parallel. Finished. This is the input impedance. Now you want to know how much is VI in terms of VS. How much is this voltage in terms of this voltage? This is what you have, gentlemen. Look, RS, RI, this is the VI, this is the VS. Okay. The voltage here, voltage divider. RI, RS plus RI times VS. So if you have a 100 millivolt peak-to-peak signal in here, this is say 2 kilo ohm, and that one, the input impedance is also 2 kilo ohm, you get half of it. It will be 2K divided by 2 plus 2 times the 100, and then you'll get half of it, 50 millivolt at the VI. Yes, sir?
So if there's no capacitor or C of E, then that RI would be plus the RE, right?
Or if the capacitor had to be counted, is this what you're saying?
No, if we don't have the capacitor.
Oh, if you don't have capacitor, you don't have coupling.
Oh no, I meant for the capacitor for the emitter.
This one, you don't, I see what you mean, at the emitter, okay. Yeah, good question here, actually. If you don't have that, now, what shall I do in the model? Remember the short you had in here? Because of the C, you don't have it. Guess what is showing up in the place of that? RE. RE would show up. That's the next subject, when we modify this transistor. We will come there. Yes, indeed. It's possible to remove this. You'll get a great advantage at some point out of it, but also you will lose something. You will lose gain badly, see? But you want instead a gain of not 150, but you want a gain of say 20, but you want good linearity. Yes, that's what we do. We take the capacitor out, not completely, but partially. In other words, look at this trick. We put the resistor there, and then put the capacitor here. So we short circuit this part, but still we leave a little tiny resistance over there. with what you put in series with the emitter. Gives you great advantages, but also the negative side of that is to lose the gain. You lose the gain. But the circuit becomes completely independent of beta. Gives you a good linear gain. Okay, so this would be the RO, output impedance. Output impedance, reference to RL, if you try to model that, when you look back, you will see RC parallel to RO. Mostly, if RO is large compared to RC, impedance looking that direction, output impedance external to RL, will be equal to just the RC. So bear in mind, output impedance viewed in the direction of the collector is the collector resistance, almost without exception. And then get into the voltage gain. So this is the one. AVI. What is AVI? AVI is the ratio of this final voltage to voltage in here, VI. It's called stage gain, the true amplifier gain. There is another voltage gain we can define from Vs to here, which we have to account for that loss, because Vs is different from the Vi. It's a little adjustment we can do there. Okay, AVI. Why is it minus Gm times RO parallel RC parallel RL, which practically it is minus Gm times RC parallel RL. So how do we get that? Again, check your circuit. Ignore this. You're ignoring that part. See, IC is the current pumped by that current source. What's the value of it? Gm times VBE. VBE is the voltage from here to here, base to emitter. So you multiply that current by parallel combination of RC and RL to get the VO. Because in the output side, if you notice, you have RL, the shorts, then you have RC, and then you have a current source in here to the ground, etc. And this is IC. IC going opposite direction. This is the VO. So according to the Ohm's law, if I want to write voltage across the two parallels is equal to IC multiplied by RC parallel RL, I should write minus IC multiplied by RC parallel with RL. Again, I said it before, but for the last time I will say why minus. Because this violates the Ohm's law when you're writing a current equation about the resistor. Do you recall we always wrote R, I going this way, positive, negative, V, so V is equal to Ri, right? This was with the convention. The convention says plus, minus, current going that way for resistor. But if somebody gives you, again, Ohm's law, V marks the current backward, you should not write that equation. If it is a resistor, you should write it V minus R. This negative is added to your equation in penalty to you violating the convention. All right? So you've got to make that adjustment, or else your equations will be messed up. You know, the laws of energy will be violated there. So when it comes to that, you get that minus. But look, what is minus IC? IC is Gm multiplied by VBE, whatever base voltage is, base emitter voltage is. But check here. VBE, base emitter, change in the base emitter voltage is exactly the same as the change of voltage at that node with respect to ground. Because this voltage is reference to the ground, like E. That node is the same as this node. So VBE is identical to VI. So if it is enough, I substitute for VBE the value of VI, and this converts to VO equal to minus GM times VI times RC parallel RL. And if you interpret the ratio VO over VI as gain, AVI, VO over VI, this will be minus GM, RC parallel with RL. Okay, so this becomes the actual voltage gain of the amplifier stage that you made. For example, if you could avoid RS, you had a source without any output resistance directly coupled, VS would be the VI. VS would be identical to VI if there was no RS. And simply the voltage gain would be the same thing. GM times that, VO over VS would be the same as VO over VI. And finally, the power gain. The power gain of that stage, AI, is equal to AI as voltage gain, as current gain. Current gain, AI, is equal to IO. IO is the current going into the RC and RL, or VO over RL, I'm sorry. IO is VO over RL. There is IO, that top corner to the right. Current going to the load, current going to the input, IL. And IO is VO over RL, II is VI over RI. If you divide them, you can write current gain of the stage is RI over RL times the voltage gain, AV. I tell you what, I hardly use that equation, and hardly you will need that equation for current gain. Not necessary at all. One you need is that guy, input impedance, voltage gain, and power gain. Power gain comes after these two. So power gain is what power goes to the load, RL, which is load voltage squared over RL. What power goes into the entire stage in the plane that red arrow is. And that is VI squared over RI. Again, if you divide it, this can be translated into the ratio input impedance divided by load impedance multiplied by the voltage gain squared. That's the loaded voltage gain. Voltage gain with RL counted into it. RL is counted in determining AVI. That's known as the power gain. Doesn't have unit. Neither power gain nor voltage gain, they don't have any units. Yes, sir?
Is that equation specifically just for that type of amplifier?
Works for everything. Works for every, just general equation. This one. You know what? Here, if you take this quantity, AFI, and you multiply by A of V, it will come up to be this equation. So current gain, defined that way, multiplied by the voltage gain, you multiply the two, current gain and voltage gain, turns into this one. So you know what, I say, don't pay attention to this one. Get the power gain formula only from voltage gain and input and load resistors, period. To make it shorter, more compact. Let me see if there is anything in here. Nothing else. We are 5:15. Okay. Let me see what is left for the next. Okay. This has to stay for the next time, definitely. It's the calculation of the capacitors. So we are doing a complete job. Going to calculate capacitors. All of them are easy except the CE. You will ask a lot of questions about that. So I need to prove something before starting that capacitor.